a demo as part of this next talk. The next talk is titled OVS Performance Measurements and Analysis by Madhu Challa from Noiro Networks.
Okay, cool, thanks. Okay, my name is Madhu Challa, and I'll be presenting OVS performance measurements and analysis today. So basically, like, this is something that I've been working on like for the past 3-4 months as to like what is the best way to measure like OVS performance, and also like analyze like bottlenecks, where there are like. So let's get started. So tools used. Basically, I used DPDK packet gen for like all the packets per second measurement. Like, I didn't have any Ixia or like other kind of tools. So I might be getting like an Ixia, like, but right now, like, this is the tool I was using. So basically, we have like OVS running on like one of the servers, and then I have like 2 servers, like which one for generating the one which acts as a packet source and other acts as a packet sink. You can actually just use like 2 machines and you can do the same thing. But I needed this setup to actually do some contract measurements, because I could then create like stateful connections and then kind of hijack the connection later from the other server. And I use netperf to measure like the bandwidth and latency for, especially when we measure like VM to VM, and all the VM to VM basically currently uses like VXLAN tunnels. For analysis, I was using like top, SAR, like mpstat, and like perf. And perf is kind of really, really useful because it kind of tells you the bottlenecks as well. You can actually analyze like which functions are kind of going up in perf top at the same time. We can actually, I'll have a short demo in the end where I can show you like how to debug that. And then netsniff ng toolkit is an amazing toolkit. It has a tool called as like IFPPS. It actually shows you like in real time like how many packets your interface is getting, like how many software queues are there, like interrupt rate and like whatnot. So you can actually like, use that tool to kind of figure out if your interrupt rate is too high, if the interrupts are getting balanced properly like across all the cores and things like that. So in the presentation, I use the term flow interchangeably. So there is an open flow, and I also refer to this unique tuple, the packet as a flow, where it's a source IP, dashed IP, source port, and dash port. I already mentioned about the servers, and that's the configuration of the servers. Then we have like 2 types of NIC cards. Like, one I'm using is the Intel IXGB, like the driver, and the other one is i40E driver. And they're both 10 gig cards, but one of them supports like VXLAN offloads and the other doesn't. And the VXLAN offload part itself, like, it has, like, the card has some issues because it's an experimental card we got from Intel. And, but we will show the numbers, like, so let's move to the next slide. Okay, so this is basically single flow and single core. So all the numbers are like apples to apple comparison. Like, so basically, we're just using like one flow, and that is the flow pretty much. OVS OF cuddle input equal to 1, and actions output equal to 2. And then the gigabits per second, you can actually see, like, I compared like standard OVS, which is basically just using one CPU again, and DPDK OVS and Linux Bridge. And from what I figured out, like OVS itself, the kernel path is very, very well optimized. I mean, I really don't see like, a lot of scope to like optimize much in the kernel path, in the sense that the only contention areas there, if you run like multiple flows, if you increase the flows and, so they go to different CPUs, is in these 2 functions, like the OVS flow stats update and the get direct transmit. And this one, it just takes a lock to update the flow stats, because I think the flow stat structure is like per NUMA node. And I tried to change this in the past, and I did not see a very big improvement. So I feel that the bottleneck is actually here. Like, so if you want like linear scaling, like as flows move to different cores, we had to fix this function, like, and see what the bottleneck there is. I think one of the bottlenecks was in the QDISC lock, and to some extent, from what I know, the latest kernels, they have fixed that, but I need to like verify like what's been fixed. So most of the drops which you see in this test case are all RX missed errors, which basically means that we are not able to catch up with the amount of packets that are coming in. So the K software QDs are at 100%, and for UDP, like as I increase the number of flows, I basically need this configuration, so the UDP port number gets included in calculating the hash, so we actually have like flow balancing across all the cores. And like I said, I stopped the IRQ balance, so it kind of always goes to one CPU in this case. So now the example here, with 4 cores, I get 3.5 gigabits per second. So you can see that it's not like scaling linearly. And these numbers are all OVS numbers. So the maximum achievable rate with this setup, like when you have many flows, is like 6.8 gigabits per second, which kind of translates to 10 million packets per second. And you would need to increase the packet size to 240 bytes to basically saturate a 10 gig link. So DPDK OVS performs like really, really great. It just gives me like 9.9 gig like right away, like with 64 byte packets. And Linux Bridge gives 1.04 gig, and so clearly like OVS performs better than Linux Bridge. Okay, so latency. The latency I was measuring using netperf, TCP-RR and UDP-RR. So the numbers here is basically, I translated them to like microseconds per packet. So you can actually see these are the OVS latency numbers, like 46 and 51. The DPDK OVS numbers are like, the latency is much lower, it's obvious. And then Linux Bridge, the latency is like 43 and 44. So Linux Bridge, for some reason, the latency is like slightly lower than OVS. It could just be noise, but I think these tests were run like 3 or 4 times, and then I took the averages. So we need to find out what is the difference there. But clearly the PPS for Linux Bridge was less. Then this is the NIC-to-NIC latency. So the way I measured this was, I run netperf on one machine and netperf server on another machine, and they're directly connected. So you can actually clearly see that this is, most of the overhead here is like, the kernel path, whatever is the overhead in the kernel path. So I feel that like OVS, like as such, like from a kernel perspective, is kind of very good because the latency numbers are also like pretty good. The last one, I think my slide is missing the thing, but it's actually the VM to VM number. So I don't know why it's missing that. But this is the number when we actually have like, 2 hypervisors, and we have a VXLAN tunnel between the 2 hypervisors, and we are measuring the latency from one VM to another VM. So effect of increase in the kernel flows. This was already covered by Joe in the earlier presentation, and I think the presentation was awesome because it actually tells you like why OVS is so optimized. So basically, like I will just repeat like what's here in the slide. Like so, the kernel flows for OVS is basically it's the cache of like all the user space flows, and all the complexity is obviously in the user space, and all the intelligence is in the user space. So OVS performs really, really great, like as long as packets hit the cache. And surprisingly, like we have done like different kinds of tests, and in all the tests we noticed that we get like very good like cache utilization. So the cache supports up to 200K flows. Although in all my tests with like 40 VMs, I've never seen the cache grow beyond like 2048 flows. Again, all our tests were based on netperf, like all the VM tests. We did not have any other like real life or like more real life benchmarks. So this test where I was using like 40 VMs, it basically has like 2 hypervisors. We basically bring up like 40 VMs on each. We have a lot of flows. We have almost like 120K like open flow flows, which then translate to these 2048 data path flows. And there are some flow misses, but it's not like all that bad. And because the numbers, the degradation when we ran with this test versus the previous numbers I showed you was only about 5%. So that kind of tells me that we are kind of getting a very good cache utilization, because the degradation would have been a lot higher, like if we were not getting good cache utilization. And the next slide would talk about the effect of cache misses, and you can see that it's actually very, very bad. So to test this, what I did was I basically disabled the kernel data path. You can do that with 2 ways. You have an appctl command to disable that, and you can set the flow limit to whatever you want. I use the may put equal to false, so the kernel data path flow never gets put. And you can see that in this test case, basically we get about 400 Mbps, which boils down to 600 kbps, which is like, and then also the user space CPU for OVS vSwitch goes up a lot. Like the load average is 9 almost, which is like it's taking up like 9 CPUs. And here I've highlighted like in perf, like what are the top consumers. In this test, I only had like 1 flow. So I don't really see the top consumer to be the NLA format, which Joel mentioned. But I think if you have a lot of flows, you probably will see that because that's where all the work happens. But here, this is mostly like, the memory copy is happening between user space and the kernel space, where you're queuing the user space packet and like all this NLA put where you're trying to basically put the flow. So this test is like the VM to VM test. Basically, we have two hypervisors, and we are running like VM, OVS, NIC, OVS, and VM. So I'm using vHostNet. So one thing you need to remember if you're using vHostNet on Ubuntu is that you need to change this file. I figured this out the hard way because without this, it actually ends up using VirtIO, and you get about 1 gig less in terms of performance. And that's pretty much the KVM command line I was using. So we basically did 3 tests. So one of them is a default Linux kernel with all the modules loaded and no VXLAN offload. And then the second test was IP tables modules removed. So for some reason, like even if there are no IP table rules configured, what I noticed is that if you have the IP tables modules loaded, it takes up time in IPT2 table, and there is some significant overhead there because we see some difference. We could see in the next slide the difference. And then the next numbers are like IP tables modules removed plus the offload, which the card provides. So these are the different tests. This is the TCP stream, the UDP stream. Then this is the reverse MERTS test for TCP. And then the TCP RR and UDP RR. And here you can see that. So I would say that ignore this number for now, because what was happening with that NIC card with offload was that there is some packet corruption going on. In other words, when I send the packets from from one hypervisor to another hypervisor, the other NIC sees all the packets. However, those packets are not sane because net server doesn't get those packets, and that's why that number is bad, because some of the packets I feel are corrupted. But let's concentrate on this number because that actually shows you that the true performance improvement when you use an offload. So with the default, obviously the default Linux kernel, and this is the number you see like Mbps per second for VM to VM. Then without IP tables, you can actually see that the UDP number has gone up a lot. And I think this needs to be fixed because we don't really have any IP table rules. The RR numbers are something I already presented in the first slide, where I converted this, this is like transactions per second, I converted to like microseconds per transaction. And then you can see the offload numbers here, so this is almost like 30% improvement, when you're using offload. And I think I should expect to see something similar with TCP2. And this is the configuration, so interface MTU was 1600 bytes, and the TCP message size is 16K, UDP message size 65K, and the RR always uses 1 byte messages. So offload, it was 40% if you basically use VirtIO, but with vHostNet, it's probably 30%. Because with vHostNet, you actually already get almost 1 gig improvement. TCP numbers are low, and that needs to be investigated. So what are the functions that show up in perf here? So there are two things. One is you can actually correlate these numbers very well. So one is when both are without IP tables, but one is with offload, one is without offload. So you can actually see that the offload is working because you basically don't see this checksum partial, because I think it's doing the segmentation offload plus the the checksum offload. The other thing I noticed is that with VirtIO, the context switches were a lot higher, but when you use vHostNet, the context switches actually go down a little bit. But still, every time this guy goes up, here, basically where there are too many signals, where the queue gets filled up, you still see a context switch because I think the VM needs to run, and then it needs to come back to the host so it can actually process the packets. So I think pinning KVMs to CPUs might help to some extent. To further improve this performance. But like I said, this is kind of, it complicates the setup because, you have way too many things to configure here. Okay, flow mods per second. So we actually have scripts, basically, thanks to Thomas. What we do there is we create an OVS environment, and we create a large number of flows, and those are configurable. In our test, we were actually adding about 120K flows or something. So this just measures how fast you can actually add the flows to the user space. This is nothing to do with the up calls per second or anything, but it's more about when I do OVS, OF cut will add flows, how fast are we able to add the flows. So that rate is pretty high, like 2000 per second. So it doesn't take all that much time to actually add like 120K flows. Connection tracking, I did a very simple test with connection tracking. Like what I had the same setup that Justin basically like showed yesterday in the slides. So what I was doing was that I had like DPDK packet gen running from like two machines, one as source and another as sink. Then I would actually create like a TCP connection, let it complete, and then I will actually like hijack the connection using packet gen and then send like packets. So I know that those packets are all going to the connection track module. So this actually just shows you the overhead of just using the module. It's about 15 to 20% when packets go to connection track module. I did not do any other testing like based on like like more flows there. And I was happy to hear yesterday that even if you add more flows, the overhead doesn't go up like much higher than this. I think it kind of scales pretty well. So this is probably like the worst case overhead of connection tracking. But this is some area where I need to do more testing, and I think once I get my XCI, I should be able to run more tests. So future work, test simultaneous connections with XCI and breaking point, and then the connection tracking feature is something, and also NAT is something that needs more testing. Then something about like agreeing with OVS testing benchmarks, because right now it's kind of not clear, like everybody tests things in different ways, and it's not kind of like when you compare results, it's very hard to compare like what the results mean. So it will be nice to actually have some benchmarks so we actually know like what we are exactly testing. And test DPDK based tunneling. That's on my to-do list, but I did not get a chance to do it. So that's it. I think we can go to a demo. I can take any questions before the demo. Yes, please.
Hi. The number with the cache misses was surprisingly good, in my opinion. You measured 600,000 packets per second. Now, I'm wondering, was that a miss on every single packet, or?
Yes, that's a miss on every single packet. We basically disabled data path completely.
Okay, that's pretty good, actually.
Yeah.
Hi, I'm just wondering, you did your flow mods. Excuse me. Did you do any testing to see the effect on the throughput on an existing flow while you were doing flow mods?
So while you're doing flow mods, if it needs a lot of revalidation depending on the traffic that's coming in, the OVS vSwitch CPU goes up. But in our test case, like basically the server is kind of like it's a fairly powerful server. Like we have like 24 CPUs, and I did not see the data path rate itself go down. I did run the test. But I think if you have lesser number of CPUs, probably you will see some side effects.
I guess it would affect your cache a lot as well.
Mm-hmm. Yeah. But like I said, right, the revalidation happens in parallel to the data path. So if they're not running on the same course, like you can actually like, maybe like you can bind the revalidation threads and, and the handler threads to different CPUs, and you probably shouldn't see you may not see any side effect at all.
Okay, thanks.
I actually have one question and another observation. So the question is, you said with UDP, with the offload card, with Intel's VXLAN enabled card, you actually see a significant improvement in UDP performance?
You should see an improvement for both TCP and UDP.
No, TCP I understand because TSO is being done by the NIC, right? But in UDP, is it just a checksum offload that's giving that?
Yeah, it should be doing the checksum offload.
Okay.
It should also do segmentation offload.
No, for UDP, what is the segmentation offload?
Because the message size is much higher, so it's going to like fragment the packet.
That's done in the kernel, right, for UDP?
No, but that's the thing that's offloaded.
Does the card support UFO, UDP fragmentation offload?
I believe so, and that's the reason we're getting that improvement, yeah.
Okay, we should probably, okay.
Because I don't really see those, I don't see the segmentation functions in perf when I run the perf.
We can probably take this offline.
Yeah.
The other thing is, you mentioned that when you've increased the number of iPerf threads, you see that it goes up to 3.5 Gbps and then doesn't scale after that, right?
Those were not iPerf threads. I was running DPDK, so I used like, there's a Lua script where you can actually increase the number of flows one by one. And so it scales, in that manner, like, so as you keep increasing the number of...
And then you have DPDK on the other end as well, on both sides?
Well, there is one source and one sink, so it's only unidirectional traffic.
Okay, thanks.
Maybe, I don't know, like, we can just do one demo, the VM to VM test, 5 minutes, 2 minutes.
I have a quick question on the scripts that you used over here. The script that you used to install 2,000 flows per second, did you use OVS or FCTL for that?
Yeah.
Yeah, I was actually going to comment that the number is actually going to be significantly higher if you used a controller that was just pushing down the flows directly. I think that you're probably seeing the overhead of doing the creation of the forking though of kettle command and the overhead associated.
Oh, we are doing the batch mode.
Okay. So I think that number, Ben and I were talking, I think that number is probably right.
Just one comment. So most of the results are expressed in terms of packet per second and percentage. So I would definitely prefer to have cycles per actions just beside, because it's very hard to understand how many cores are involved and in the different schema, and especially for the Linux bridge. Did you pin the IRQ just on one CPU to make sure that you just have one CPU? Or
yeah.
you boot your machine with just one CPU?
Yeah.
Oh, okay. Okay, sure.
Yeah.
But I think because when you said you have an improvement of 10 to 15%, that's good. But cycles are really more accurate. I think from version to version, because the ratio will change if something has changed, but a function will still be traversed with the same number of cycles.
Yeah, that's why I try to keep the test like very apples to apples. Like everything was pinned to one CPU in the first test, and basically we are only testing on one CPU.
Okay, thanks.
I agree. I think we need both the performance metrics. In your test, did you have? I was wondering whether you were running actually anything on the VMs and what the impact of the any application running on VM on the overall system performance.
The VMs are configured to run with two cores, and I was not running any applications other than NetPerf's client and server. But if you run VMs if you run other stuff on the VMs, like sure, like your performance may be impacted, but that's basically because of the VM, like not here. My goal was to really measure like the OVS throughput, not exactly like what happens in the not
What is
the
your
VM
assumption
load.
here? You're running the OVS on a dedicated core, or is?
So we have 24 cores on that system, and I was just doing a VM to VM test with with the VM taking 2 cores. So as such, the VM wasn't interfacing or interfering with OVS.
Because I'm interested, because once you have real system performance, then you get into actual cache flush.
Sure.
Flush
I mean,
backs
it really depends on how many VMs
that's where
you're...
the latency comes into picture in terms of what misses.
Absolutely. It depends on how many VMs you're running and how busy OVS is or other things. Yeah.
All right. Thank you.
Okay. So basically, I have two machines here. Like we'll do the VM to VM test first because the DPDK test takes more setup. So what I'm going to do is I'm going to basically start OVS on these two. And then I'm going to basically create the VXLAN tunnel. And what this would do is it will also start one VM on each of them. So now we can attach to the VM on each of them, on each of these machines. And the final thing we need to basically create we need to bring up the interface that we are going to use for the tunnel. Okay, so we have connectivity, and now we should be able to run the TCP performance test. So for measurement, like when I'm trying to profile something, I basically keep the time interval really high, because then everything starts showing up in perf more easily. So we could go back to so here you can actually see this is basically where the copies are happening. And this is one more thing that we need to optimize on, that is the fib table lookup. Right now we do a fib table lookup every time we need to send the packet to the other host And this test should actually give you that this is the throughput basically which we are getting. So any questions on this? Pardon me? Yeah, it is a flow. We are using flow-based tunnels here. Good point. Thanks.
So we have time for one question if anybody has one. All right, let's thank our speaker.
Thank you.